Hi, I'm Shao. When we look at an image, at a photograph, our gaze roams through the different elements depicted in the two-dimensional representation of the scene. We are first drawn to areas of high contrast. Then from there we start moving our eyes in circles, concentrating on objects or subjects we can recognize. Human faces are a strong point of interest to us. Instances of written text, especially if it's printed and clear, another source of information that can give us an idea about what's going on, about the context of the photograph we are looking at. Then we look at relations between different points of interest in the photograph. The more relations we find, the more we enjoy the photograph. That's a general rule. However, there might be just too much detail for us to process. That extra detail, especially if it's over-accentuated edge detail or micro detail, hinders our roaming process. Our natural vision uses a hierarchy of contrast. We are much more sensitive to macro contrast than to micro contrast. Our eyes do not see small details very well. Our brains have evolved to fill in the blanks, to be able to imagine details that are missing from what we actually see. Now, an image is a two-dimensional thing that is striving to depict a three-dimensional space. When we don't see the small details very clearly, we imagine the missing parts. Now, imagination, unlike our vision, works in all three dimensions. I would like to argue that a balanced contrast or a lack of accentuated edge detail actually improves or enhances our imagination of the z-axis. We use cues such as variations in brightness of surfaces to interpret their curvature and thus their shape, their form. Moreover, we can more clearly imagine distances in the scene based on those interpreted curvatures. The hierarchy of contrast is depicted in what we know as the MTF chart. That chart describes the effect of frequency on contrast. There are many ways to draw an MTF chart. What lens manufacturers usually provide us with is a chart describing the change in contrast as related to the distance from the image center towards the corner. Typically, the contrast is depicted in two different frequencies. Low frequencies, such as 10 lines per millimeter, and high frequencies, such as 30 lines per millimeter. Contrast is measured at two different axes, the sagittal or radial axis that goes from the center of the lens's projected image circle to the periphery, and circular axis. The top pair of lines in the chart that describe the contrast level at a low frequency depict something that I would equate to the clarity of the overall image. The higher those lines go, the more glossy the image will look. The lower they go, the more matte the image will look. It will have less contrast, which is not a bad thing in itself. It's a matter of matching the tonal range of the scene and the mood you would like to convey in your photograph. The lower pair of lines that depict the contrast at high frequency are related to the accentuation of edge sharpness, or the contrast of very small details in the scene. The higher those lines go in the chart, the more emphasized the edges are. The lower they are, the more subdued they look. Most lenses would still depict small details, but they will not accentuate them so much. When those lines are at around 50 to 60% of the total possible contrast, you will get an image that imitates the way we see the world with our native vision. The hierarchy between the gross contrast of larger surfaces and the contrast of small details will be preserved, and the image will look more natural to our eyes. The lenses I like the most have a low frequency contrast of around 90%, but the high frequency details only reaches around 50 or 60%. That hierarchy of contrast lubricates our gaze through the image. When edges are too prominent in the image, they disturb the movement of our eyes through the image. We are obliged to concentrate on the details, on the two-dimensional level of the photograph. We cannot really imagine the depth. Our eyes are looking for gradations that would give us a good cue for the forms in the scene, for the three-dimensional shape and relations, not for the two-dimensional shape that is defined by outlines. To borrow some terms from culinary jargon, we like looking at buttery rendering rather than crisp, choppy rendering. The preservation of natural contrast hierarchy depends a lot on lens construction, and specifically on the chemistry of glass used in a lens. Low density glass we know as ED, or extra low dispersion glass, with its many varieties, makes edges more contrasty. It makes the images look crisper. On the contrary, high refractive index glass, which is denser, heavier, it contains heavy metals such as lanthanum, tends to resist light. It actually slows the travel of light through the glass. It diminishes the acutance of outlines, of sharp details. So it contributes to the buttery feeling of the rendering. Complex groups in the lens, groups that contain more than one single glass element, two or more cemented together, act as high index glass, because you can look at them as a single element in which the angle of light changes while it travels through it. So a multitude of complex groups helps preserving the natural hierarchy of contrast. You can easily see it in lenses such as this one, the Typoc 35mm f1.4, that contains 4 complex groups with no extra low dispersion elements. Nevertheless, lenses such as this one, which is quite a new lens, are a rarity these days. I think that 95% of the lenses introduced in 2024 and 2025 were made with precision, crispness in mind. Those lenses are very well corrected for all kinds of aberrations, and therefore they look a little bit flat. The outlines, the edges are emphasized, and therefore you cannot really imagine or interpret the depth of a scene shot with those lenses. There are 2 reasons for the prominence of flat lenses in the industry. The first one is the increasing resolution of sensors. To resolve the entire potential of those new sensors, you need a very high resolving power, which is assisted by the use of a lot of low density glass. The second reason is more prosaic, maybe. Optical engineers are employed in order to achieve perfection. I'm afraid they do not take much notice of artistic considerations that require a lower contrast at very high frequency levels. Unfortunately, the market itself, the users of cameras, of optics, comply with this trend, gaining more and more clarity. With clarity goes the over-accentuation of edges and flattening of rendering. My own views about optics are quite unusual, I know. Most photographers do not see the importance of hierarchy, of contrast. They do not quite understand the relations between lens construction and rendering. So I try to explain it over and over again in order to gain some traction. I found some allies in an unexpected place. Among the cinema crowd, video is seldom cropped. You tend to look at the whole image taken by the imaging pipeline, your optics and camera. And I think that when refraining from cropping too much, or from looking at the image at the pixel level, you can see the forest or the trees, and you can appreciate the drawing style or rendition of your optics in a more accurate manner. Cinematographers clearly understand the distinction between clean and character optics. In photography, we refer to a clean rendering as a well-corrected, flat rendering. Character is a more general, more generic description. But I tend to look at it as a more true-to-life rendering that accentuates gradations rather than outlines, and thus allows us a better perception of the three-dimensionality of the scene. But even in cinema lenses, the trend has been towards more clinical rendering style. Let's take THIPOC as an example. THIPOC is a branch of a very well-known cinema lens manufacturer, DZO Optics. And as such, they do know their stuff. They don't necessarily strive for the crispest rendering they can achieve. They are perhaps communicating with cinema makers. If we look at their Chimera line, which is a set of f1.4 prime lenses that are quite small, there is some variation in the choice of glass types inside this line of lenses. Some lenses are clearly designed for a more true-to-life, more dimensional rendering, and others are designed with more crispness in mind, so they contain more ED glass and not as many complex groups. In my efforts to predict the rendering of a lens by taking into account its construction, I came up with a score. I call it the dispersion score. The higher it goes, the more true to life the images produced without lens will look. The lower the value, the more clinical, corrected the images will look. And that score was also validated by tests I did on this channel, comparing different lenses with different scores. Dispersion score is calculated by subtracting the number of low dispersion elements from the number of complex groups in the lens, and dividing that difference by the overall amount of elements in the lens. A score exceeding about 0.14 will result in a more true-to-life rendering. Images will be on the poppy side. A score smaller than 0.14 will predict flatter, more precise, clinical rendering. So I calculated the dispersion score for each of the Typox-Chimera lenses. There are 5 of them: 21, 28, 35, 50 and 75 millimeter in the entire set. And I plotted the dispersion score against the high frequency contrast taken from the MTF charts published for those lenses. Those two variables were very well correlated, with an R-square value of around 0.99. It means that lens construction explains almost the entire variability in the preservation of contrast hierarchy. The higher the dispersion score, the lower the contrast at high frequencies, and the more pleasing, to me at least, the images look. The distribution of dispersion scores within this line of Typox-Chimera lenses does not make much sense, does not relate very well to focal length. The shortest or widest lens in this series, the 21 millimeter, has the highest contrast level, or the lowest dispersion score. Then the next wide lenses, the 28 millimeter and the 35 millimeter, are built differently. They have a much higher dispersion score, and they are quite poppy, which manifests itself in a low contrast level at high frequencies, between 55 and 60% for most of the projected image circle. Then the 50 millimeter and the 75 millimeter have a lower dispersion score again, which manifests itself in a higher contrast level at high frequencies. So those lenses are more clinical. There is not much sense if you try to look at focal length. However, I also looked at the announcement dates of those 5 lenses. And it appears that the later the lens, the lower its dispersion score and the higher its contrast level at high frequencies. So the trend towards a more clinical look must reflect a demand coming from the market, a preference for this type of optics. I'm a little bit disappointed by this trend. I honestly cannot understand why we lost the craving towards a natural, more dimensional look in our photographs, in our footage. It is disheartening. Fortunately, there is a vast catalogue of older lenses that were not designed by computers, and they do have a tendency to make the images more pleasing. Another advantage of using such lenses is they are becoming quite affordable. Even lenses that a decade ago were too expensive for mortals to own and shoot. But now, with the change of heart that occurs in the market, and with mirrorless technology taking over, those lenses are coming out of fashion, are more accessible. Hopefully, more and more people use them and learn how to make the most out of their very pleasing, rounder, more dimensional rendering. Right, I think that will do for today. If you want to support my channel, if you enjoy the content of those videos, please consider buying me a coffee. There's a link in the description below. It's a nice gesture between gentlemen. Thank you for watching. See you again soon.